Hello, everybody, and welcome to episode 76 of I Wish You Were Dead, a podcast about things that used to be alive. No fear this week. It is just me over here and Gavin. Gavin, how many states have you been to?
So we were talking about this before we started recording, and it depends what you mean. Mike defined it as states that you have spent time in, which basically means no plane layovers. And also, if you've just driven through the state, only stopping to get gas, that also doesn't count. So,
right. If you've done something that actually counts in the state. If you've just hung out in the airport, no. If you've only driven through or just gotten gas, no. But even just stopping to get a bite to eat or I think my bar is pretty low, but it's more than just being physically present in the state.
So when I drive, I'm very efficient when I drive. I will drive. And this is relevant because actually today, the day this comes out, I've just left on my travels from California to moving to Pennsylvania for the new job.
Oh boy.
So if it were up to me, I'm very efficient when I drive. I would drive 12 hours, only stopping, I would fill up with gas in the morning, stop once for gas and also food from the gas station, and then and get gas at night. So I will drive 12 hours, only stopping once, and that is peak efficiency. However, that is not how the folks traveling with me want to travel for some reason. I don't know.
I mean, yeah, when you have this kind of big cross-country trip, you might want to, see some things.
If you could be one thing, you should be efficient. In my opinion. I think we're going to stop and see a couple of things, but we're also traveling with a dog and a lizard. And it's summer when it's hot. So when and where we can stop is a little up for debate. But anyway, long story short, if you're only counting states that I have spent time in besides stopping to get gas, roughly 21-ish, 22-ish.
Okay, that is significantly more than me. And the only reason I wanted to bring that up today is for just today's in history.
All right.
Gavin, you're familiar with the original 13 colonies that became the 13 states?
I sure am.
Do you have a guess as to what the 14th state in the United States was?
14th state. I believe... I want to say Vermont.
Great work, yes.
Because I know it's a northeastern one. But yes, so my first thought was New Hampshire, but I'm no, I think they were a state.
Yep, New Hampshire was originally a state.
Yeah.
And Vermont was actually sort of quasi its own country for a little while.
Oh, okay.
And then eventually became the 14th state. That is not the today in history.
Oh.
The today in history has to do with our 15th state. Do you have a guess as to what the 15th state in the United States was?
15th state. Okay.
Yes.
Okay, well, we ruled out New Hampshire.
Correct. You have no shot of getting this, so just take a guess.
I have no shot. Okay. I'm guessing it's a state that no longer exists and has been since split up.
No, that's not true. So it is still a state today.
Can you give me a year?
1792.
92. Tennessee.
Oh, very close.
Dang.
I think, actually, if I'm being honest, I actually don't know how close you are because all those states blend together for me.
Was it Alabama?
On this day in 1792, Kentucky was admitted as the 15th state.
They share a pretty good-sized border.
Yeah, exactly. So today in history, Kentucky becomes the 15th state, and that's those early years of those states that got admitted. I don't know why, but it's kind of interesting to me, just kind of looking through what states got admitted in those early years.
Yeah.
So
and Kentucky's been, throwing out winners ever since. That's sarcasm for anyone who's not aware.
People in Kentucky couldn't even spell the word winner.
Well, let's not go that far, but to say they're to quote a person, they're not sending their best.
Here, actually, I disagree. I think they are sending their best.
Oh, that's very mean, but potentially accurate. Anyway,
I was going to say something even meaner, but I guess I should probably stop right now.
Yeah, let's.
We have an episode to get to today.
We sure do. So today's probably going to be a relatively short episode, just because we're trying to bulk record a decent number of these ahead of time before I leave. So obviously, if I have just left California for Pennsylvania today, there's a solid chance that we've already recorded next week's as well, because that's a pretty long drive if you're not familiar with North America. But today we're going to be talking about something very fundamental to geology, like definitely something you go over during at least the intro week of like Geology 101, and that is the rock cycle.
The rock cycle.
Yes. Something that
most I
feel like
people, I've heard of this before.
Yeah. So New York, as I've since learned, is relatively unique in that New York requires an earth science class in high school. A lot of states don't. And so if you did your high schooling in New York, especially relatively recently, you've probably been forced to learn about the rock cycle. So the rock cycle is more or less, it describes the interactions between the three main types of rocks, how they form, how one type of rock forms another kind of rock, and the processes that go from rock type A to rock type B to rock type C, and so on. So it's a very fundamental thing to understand in geology, and it's one of those things that's like, can be as simple as you make it, or as complicated as you want to make it.
So this is something you can get 80% of the way there with like 20% of the effort.
Sure. I don't exactly know what you mean by that, but
what I mean by that is that you can make it as simple or as complicated as it wants to be. And if I want to get like 80% of the way there, or like if I want to just learn, a good amount, I can do that without a whole lot of effort.
Yeah.
And then I can get much more complicated, and, it's going to take a lot more work for me to learn that remaining 20% than it did for me to learn that first 80%.
Yeah, I think that's a good way to put it.
Yeah, that's perfect. So how deep are we getting today?
So we're going to get basically as deep as you would in like an intro geology class.
Okay. Shout out, by the way, to my...
go ahead.
Quick shout out. You mentioned earth science. Shout out to my 9th grade earth science teacher, Mrs. Cormanic, aka the Cormaniac. There was nobody else that called her that except for me, but damn it, I still remember.
But yeah, so at the end, we're going to get a little more into it than you probably would in an intro class, but that's just a very like a case study. So one specific sort of example. But yeah, so let's talk about the rock cycle. So I mentioned earlier the three main types of rocks. Mike, would you happen to know what those are without looking at our Google Doc?
Yeah, I actually think I know this one. So you've got, do you want me to say anything about them or just the names of the three kinds of rocks?
We'll just do the names.
Okay, so sedimentary, igneous, and metamorphic.
You got it.
I feel so accomplished. This just, you know what? I'm actually not going to tell this joke. Keep going. I'll save it for later.
All right. So, and we're going to go through lots of examples of what these types of rocks are, just because I think that is helpful in picturing them sort of in your mind. So first, let's do igneous rocks, because those are typically the first ones to sort of start off the rock cycle with. So igneous rocks are very straightforward. They're in my opinion, probably the most straightforward as, regarding how they form of the three types of rocks. So igneous rocks are formed by the freezing of lava / magma / water, technically. And that's it. It's just frozen, cooled, molten rock.
When you say frozen, we're not talking about like typical temperatures that would needed to freeze things that we normally think of. It's like just normal temperatures.
That
right?
Depends. So each mineral, and therefore every type of rock, has a melting point. And for the vast majority of rocks, that is very, very high. I don't have any off the top of my head, because this is not typically what I deal with. This might surprise you, but fossils are not particularly common in lava rocks. Lava tends to just burn things. There are fossils from igneous rocks, but they're in the vast minority. But something that I will use for these rock types example is how I said water technically, because ice is a mineral. And depending on, because like the term rock technically has a definition, but can be played pretty fast and loose with. So technically, large bodies of ice are rocks.
Large bodies. Okay. This is like the continent problem here.
Yes.
How large is large?
Exactly. So some examples of igneous rocks in general, and I'll get a little more specific about the water in a minute. But so common examples that you've probably heard of, at least for igneous rocks, are things like granite. Granite makes up most of the continental basement rock, so the very bottom chunk of rock on all the continents is granite. It also makes really good countertops. Basalt is an igneous rock that is sort of the oceanic equivalent to granite. It makes up the bottom chunk of all the ocean crust. Obsidian and pumice are also igneous rocks. They form from their glass, so it's lava that cools fast enough for crystals to not form. And then lastly, for the water example, would be like a frozen lake. If you have like a lake or a puddle that freezes all the way through, that would technically be an igneous rock if you want to be super pedantic about it.
If I just go to my freezer though and like freeze up the ice tray, does that not count?
No, that'd count.
Okay, so wow.
Again, this is the real like lawful evil version, or I guess like chaotic neutral maybe. I feel like this is more chaotic energy.
Yeah.
But technically, like, and the ice being a mineral is not like a technically thing. Like it for sure is. But what rocks are made out of ice is a little, again, like playing fast and loose. And I'm not meaning this to be confusing or anything. If people are confused, if you want to ignore all the stuff about water, because water does a lot of weird things, just focus on like the granite, the basalt, the obsidian stuff.
Okay. I mean, I've heard water. This is one thing I remember from the Cormaniac, was just like the way water freezes is incredibly strange because it expands when it freezes, and that's not normal.
Yeah, and that was going to become relevant, but I was going to have something about that later on in this episode, but I decided to cut it because I'm like, I don't know the chemistry well enough to talk about it confidently.
Fair enough.
But moving on to my personal favorite rocks, the sedimentary rocks, which are less straightforward in how they form than igneous rocks, but they're like the middle of the road. But I like them because it's where you get all the fossils.
I was gonna say these are the former plant matter, right?
No, well, yes, like things like coal are sedimentary rocks, but that is the vast minority of sedimentary rocks.
Okay.
So sedimentary rocks are rocks formed by the accumulation and consolidation of sediments at Earth's surface into a rock. Basically, it can be inorganic or organic. Common examples would be like sandstone. Not at all biotic. That can perfectly well form in the absence of any kind of life. Just pieces of sand glued together. Other examples are things like shale, which is really similar to sandstone, but the grain sizes is just much, much, much smaller.
Okay.
Limestone, which is, it doesn't need to be, but is, especially, these days when we have lots of life around, life is not technically required to form limestone, but most of the time, limestone is formed by life. If that makes sense.
Say that one more time.
So, life is not required to produce limestones, but most of the time, limestones are produced by life.
Okay, so it can be produced other ways, but it's usually going to be around something. Okay. So it sounds like with sedimentary rocks, there should probably be like one of the first groupings should be like made from organic versus inorganic materials. Then,
yes and no. So
or is that not a distinction? That's okay.
No, there absolutely is a distinction.
Okay.
The first distinction that I would make would be whether it's an evaporite or not. So if you have really salty water and all the water just evaporates, all that salt stays, it doesn't evaporate with the water. So that salt, like if you had just a cup of salt water and all the water goes away, the salt crystals at the bottom is technically a sedimentary rock. Right. And that's there are lots of minerals that form that way. Like rock salt forms that way. Things like gypsum typically form that way. But that would be the first distinction I would make. After that would be whether it's, a carbonate is typically how that's referred to. The ones that are typically, but not always, made by life or, life adjacent.
I can't escape the feeling here that the definition of rock that I guess exists is so overly broad that the category of rock does not seem to be actually useful.
Pretty much. Yeah.
Okay. Wow. This is disappointing. This is a downer. All right.
I mean, like I said, there is like a technical definition of a rock, but yeah, that can be played with very fast and loose, as we've shown.
Right. Yeah.
And the, like I said, coal is also another example of sedimentary rocks, but the fast and loose example for sedimentary rocks that I have is glaciers. Because you can think of each individual snowflake as like as a grain of sand, and all of that just being piled onto each other and cemented, stuck together, forms stuff like glaciers. So technically, glaciers are just a big sedimentary rock.
I feel like that makes sense just on that scale. It's definitely hard to think of just frozen water as being a rock, but on that scale, like, oh yeah, that I can see how that makes total sense.
Mm-hmm. And then lastly of the three is the type that I find the most confusing, and it's really funny. I remember having a conversation with the person who taught me like intro geology when I was in community college. I needed some like career advice, so we had like a Zoom call, sometime last year when I was still in South Dakota. And she was like, yeah, so here's igneous rocks, which, it's lava. You can always make that pretty cool. Here's sedimentary rocks. She was a biogeochemist, so she was, fossil adjacent in what she does her research on. So she's like, sedimentary rocks, where all the fossils are. And here's the metamorphic rocks, moving on. Because they're really abstract in how they form. You can't go somewhere really and watch one being formed. You can go to Hawaii and watch a volcano erupt and watch that lava cool, or you can go to the beach and pick up a fistful of sand and imagine how those could just get compressed together and stuck together. How metamorphic rocks form is very abstract to most people, including me. But metamorphic rocks are rocks that are formed from other rocks, so there has to be a rock to begin with that is put under like unimaginable amounts of heat and pressure, but not enough heat to melt it. So it cannot melt if it is a metamorphic rock. If it melts, it becomes an igneous rock. Yes. There is some like partial melting that can happen, but then that sort of gets wibbly wobbly as to like how much melting is partial melting.
Right. I was going to say there's probably a little bit of like some blurry lines.
Yeah, for sure.
Kind of around that transition, but okay.
Yeah. And so basically if you take like a sandstone and you bury that very far down, or you have like a sandstone layer that happens to be where two continental plates are colliding and building some mountains, that's the kind of force that's required to make metamorphic rocks. And some very common examples of that are things like gneiss, which is very commonly used for jokes about geology.
Yes.
Schist as well. A couple more common ones that you might have heard of are slate, I know I am just old enough to remember writing on slates in like early elementary school.
What do you mean writing on slate? Like
little mini chalkboards.
Yeah, okay, I did that.
Yeah, those are. I mean, I'm sure it depends on the manufacturer, but those were especially old school times because ours were like from like the 50s. Were made from slate,
mm-hmm.
And marble is also a metamorphic rock. But the water example, I kind of had trouble because I'm like, where does water go through these kinds of stuff without just melting?
Right.
And the only thing I could think of would be like the bottom of a glacier. Because the bottom of a glacier, while still frozen, is still kind of wet. And is just like structurally, like crystal-wise different than like the top of a glacier. So, not the best example. But that's probably the closest you're going to find.
I was going to say, it's probably a hard one to find examples for.
Right. And so those are the three main types of rocks that we're going to be talking about here. So it's just the main thing you need to take away from those definitions was how each of them form. So igneous rock is freezing liquid rock. Sedimentary rocks is the accumulation of little bits and pieces of other rocks. And metamorphic rocks is the squeezing and heating of other rocks. But you'll notice to form each of those, there needs to be a first rock. Right?
What do you mean?
There needs to be a rock for something to happen to. So there needs to be a rock to melt to form an igneous rock. There needs to be a rock to break down to form a sedimentary rock. There needs to be a rock to metamorphose, to heat and pressurize to become a metamorphic rock.
Oh, God, motherfucker.
Which is why it becomes a cycle.
You know the question I'm about to ask. You know what question I'm about to ask, though, right?
What came first?
Yes.
I think it's pretty well established that it was igneous rocks first, just because the Earth was hot.
Mm-hmm.
At the beginning, the Earth was really hot and everything was really molten. So part of it probably cooled, but as soon as it would cool, it would start breaking down to form sedimentary rocks, which is part of the cycle that we'll get more into the exact pieces of the cycle in a little bit.
I guess this makes actually more sense because like the entire Earth was just like on fire for the first
a ball
like,
of molten rock. Yeah.
Yeah. Right. Okay. So actually, part of me was being like, "Oh my God, where'd the first rock come from?" And like the entire planet was rock. Yeah,
right.
Okay. This is less of a mystery now that you've explained it this way than I originally thought.
Okay. Good. That's what we strive for.
That's what you strive for.
Exactly. So, this whole process of the rock cycle is driven, as all things are in geology, by plate tectonics, episode 39. Plate tectonics is the driving force behind all of this. Every process that we're going to talk about, more or less everything that happens on the planet, can be traced back to, with only a couple of steps, back to plate tectonics. I will say there is the caveat that rocks existed before plate tectonics, and we don't have a great understanding of how the rock cycle kind of worked before plate tectonics, to my understanding. Obviously, there were rocks to cool, and then those would break down, but how do rocks get recycled without plate tectonics? I don't believe there's too much knowledge about how that happens. That's getting really into the theoretical side of things, and we're not really going to touch on that.
Thank you.
Plate tectonics is the grand mechanism that effectively controls all of the abiotic factors on Earth in one form or another. It drives the formation of all three of these rock types, and because of that is just really fundamental to understanding the rock cycle to begin with. So, let's go over the rock cycle, quote unquote, from the beginning. It's a cycle, so there really isn't a beginning, but from the beginning.
All right, let's do it.
Let's say that a volcano erupts in the Andes Mountains in South America. And I'm using that specifically because they're volcanoes that are really close to a an active margin where there's two plate boundaries doing some funky stuff together. And that's important for a reason. But we'll circle back to that later. So, volcano erupts. That molten rock cools and solidifies into igneous rock. Cool. That rock immediately starts breaking down both physically and chemically. Physically, it's called erosion. That's when the little bits and pieces are physically transported away from where they were broken off of. You see sand blowing around. You see, silt or, gravel being moved down a river or something. That is erosion. Weathering is the chemical side that we've touched on a handful of times in this podcast, mostly as it relates to carbon dioxide. We'll talk about that more toward the end of this episode. But so as soon as that rock cools after being erupted, it starts breaking down. All of those bits and pieces will some way or another make it down into the ocean. Some will end up on land, but we're not going to focus on those right now. So they'll go west out into the Pacific Ocean. And if they're sand, if they break down to sand size, they'll form, for example, a sandstone. All those different layers of, the sand being washed into the ocean by rivers or stuff like that will just cause these layers and layers and layers of sand that over time, all that weight plus, water is heavy. Water presses down on whatever's underneath it. All of that will press the sand together and compact it and lithify it into a sandstone.
What does lithify mean?
Basically, like, to turn it from just like loose beach sand, for example, into something that will not fall apart on its own, more or less.
All right, so like compressing it. Okay.
Yeah, and that can happen in a number of ways. Like the sand grains can be cemented together. That's part of how we classify different types of sandstones, because there's many, many different kinds of sandstones. But like how well cemented it is, what type of, what makes up the cement. It can be made out of a number of different minerals. But we're not getting into that today.
Not yet.
So all of that compaction presses the sand into a sandstone. Because it's now in the ocean, at the bottom of the ocean, on this plate boundary, the ocean, because ocean crust tends to be denser than continental crust, the ocean crust will subduct, or basically be sucked underneath the continent. When this happens, that creates a lot of heat and pressure because, like I said, these are continent-sized bodies and therefore have continent-sized weights and pressures behind them. So that sandstone will then be lithified and chemically altered by this heat and pressure. And as that happens, it could then, if the sand is very, very like quartz rich, could then be metamorphosed into something like a quartzite. A type of metamorphic rock that is basically just entirely quartz, more or less.
Entirely quartz, more or less. Entirely quartz would be a good name for a band.
I'm pretty sure there's a number of like Facebook groups that are titled like band name called it, or like thanks for my new band name or something. Something to that effect.
That's one of my favorite things as I'm just like, going through whatever topic. It's happened thousands of times as we've been doing this podcast. Just been like, man, that'd be a good band name, or I want that as a bumper sticker, or just like completely out of context. I love that kind of stuff.
You should like jot those down. Maybe at some point we'll open up a I Wish You Were Dead store and sell bumper stickers. I don't know.
I can't tell you how much I would love to do that. Although, to be honest, it'd be hard to do better than our logo.
That's fair. Anywho,
that really is cool. Anyway, all right, yeah, we're doing science stuff.
Yeah, so we have this quartzite, this metamorphic rock, but the continent isn't just going to stop and let that, quartzite be uplifted to be discovered by some geologist. That does sometimes happen, but a lot of times, and conveniently for this example, it will just continue to be subducted until it gets far enough down into the earth that it just melts. And then that is where the new lava, or magma because it's underground, comes from to be erupted out of the Andes once again to start the cycle over. So, very briefly, lava erupts, cools, breaks down, collects, and is cemented together, then gets further buried, heat and pressure changes its chemistry, it gets further buried again, melts, and becomes lava again. That is the basic life cycle of rock. However, it gets way more complicated than that because it's not really a rock cycle, even though that's what it's called, as much as it is a rock web. Because any type of rock can be turned into any of the other types of rocks, including itself.
But there's only like 3 options here, so I feel like calling it a web implies, there's, a whole bunch of different ways this could go versus it's like...
Oh, there is.
Okay, do tell then.
So, for example, say that sandstone, so we get to the sandstone part, that sandstone, instead of being subducted and then melted, it could just be uplifted, as part of the Andes, and then eroded again. So it could go directly from one type of sedimentary rock to a different type of sedimentary rock. Or, say it gets metamorphosed into that quartzite, but instead of being shoved further down, that gets uplifted, and then that quartzite breaks down into sand, which then just becomes another sandstone. So instead of needing to be a cycle, it can circle back to basically any of the points on the cycle.
Right, and it sounds like part of this is, as far as it being a web, is not just those 3 main categories, but the fact that they can change into like any of the other like types of rocks beyond just igneous metamorphic. Okay, in that point makes way more sense to think of it as a web than a cycle if we're including all of the like types of rock and not just those 3 big categories.
Right. The only exception that I can think of is that I think it would be really hard. I'm sure that there is a way to do it, but I had trouble thinking of an example of a sedimentary rock directly becoming an igneous rock without being at least kind of metamorphosed first. But
okay, sure. Exceptions to every rule, whatever.
Right, but like I said, Earth's a big place. It's a very dynamic, complicated place. I am positive there is a way to do it. I just couldn't think of a good, clean example. So that is the basics of the rock web. That was just very subconscious. I meant to say rock cycle, but rock web came out.
I mean, we said rock web's a better way to talk about it.
Yeah. So, and this could be, the more you look into it, like I said, there's an infinite number of ways that this could go. And it's one of those things, because it is the basic thing of geology. You run very quickly into many, many, many vocab words, and you can just go down a very, very, very deep Wikipedia rabbit hole. It can be as complicated or as simple as you want it to be. And that's almost as simple as we want it to be. But I want to break down a little bit more about plate tectonics and then go into a bit of a case study into other things that get cycled with the rock cycle. Because it's not just rocks. So,
okay.
Because plate tectonics is, like I said, the driver of all of this stuff, here's kind of how. So the plate tectonics are what create volcanoes. Like I said, the Andes, caused by 2 plates coming together. Things like the Himalayas, same thing. It also, volcanoes are formed when plates move apart. A really good example is the mid-ocean ridge in the Atlantic. That's caused by several plates moving away from each other, but in the North Atlantic, at least, it's the North American plate and Eurasia moving away from each other, and then as you move a little more south, it's South America and Africa moving away from each other. So there is effectively like a several 1,000-kilometer long volcano running down the middle of the Atlantic, and that is constantly churning out new igneous rocks, mostly basalt.
And that's from all the the magma, just the melted rock that's just in the center of or I shouldn't say the center, but in the mantle of the Earth.
Right. Yeah. Exactly.
Okay.
And so as the continents move apart, something, magma from the mantle needs to come up to sort of fill that gap, right?
Mm-hmm. Right.
So that is how volcanoes form for the most part. There are some weird exceptions, but tectonics form volcanoes almost all the time. Plate tectonics is what uplifts rocks so that they can be eroded. If rocks are in the ocean, they don't really get eroded, which is a big bummer because I'm sure there are some great fossils that are just chilling in rocks that are under the ocean that we probably will just never get to, because that's a big way to lose fossils, is if it's just never uplifted and then gets subducted. So I'm sure there are some great, really neat fossils being subducted under South America right now that we're just never going to get to see.
We should, side note, I think this should be a good episode, is just like deep ocean biology or something to that effect. Like I guess I don't know exactly what I'm asking for, but there's something kind of cool and creepy about just like those extremophiles that are at the bottom of the Marianas Trench or whatever.
Sure, we'll jot that down on the list.
Yeah, absolutely.
Moving on, plate tectonics are pretty much the only natural phenomena that create enough force to create metamorphic rocks. There are a couple other examples. For example, I think that there are some metamorphic rocks caused by asteroid impacts. I think technically those are metamorphic rocks. Some of them.
I guess that would make sense.
Right. So
it's probably not hot enough to melt, but yeah, I can see that.
Well, and metamorphic rocks are a very big spectrum, because you can get low grade or high grade metamorphic rocks, which just is how hot they got.
Right.
So you can put something under a lot of heat and it will change chemically, even if there's not a lot of pressure. Or again, I'm sure there is like a technical way to put something under a lot of pressure without a lot of heat, but generally those go together. But anyway, all of that's caused by plate tectonics, and that's what moves this web. So now that we have the rock cycle basics sort of done, I want to touch on how the rock cycle affects other natural cycles that life needs to function. It's a paleontology mostly podcast. So let's actually talk about some life stuff. So the one that we're going to sort of use as a case study here is carbon. Carbon is something that most people are fairly familiar with. Most other natural cycles work in a similar way, not the exact same, but for example, like the nitrogen cycle is something that's really important, but nitrogen is much more abstract to people than carbon is, just because we talk about carbon a lot. But all life needs carbon. You've probably heard the phrase that of carbon-based life forms. That's because
I remember the Jimmy Neutron movie.
Yeah, exactly. So all like molecules, or at least like macromolecules that are made by life, I shouldn't say all, the majority that are like made and used by life are centered around carbon. Carbon's a really cool element because it can bond with just about anything. And that makes it really useful for life because you can use it for basically whatever you need to use it for. It's a very adaptable element. And because it can bond with so many things, that also makes it really common in rocks. Lots of rocks, as I mentioned before, there's entire categories of minerals that are focused around carbonate or carbon. A big section of sedimentary rocks, like I said, are called carbonate rocks because they're formed centered around carbon. And so here is more or less the cycle as it applies to carbon and how the rock cycle sort of affects that. So as I think we've talked a bit in maybe our fossil fuels episode, that for a while it was a very common thing for like climate denialists to say that like oh, humans aren't doing this, it's volcanoes, or that's where all this CO2 is coming from. I feel like that's something that most people have maybe heard.
What is it again?
That a lot of the like carbon dioxide that we're putting into the atmosphere is actually from volcanoes.
I have heard that from people that generally tend to be more climate deniers. I think
Right.
isn't that one of those things that like is true, but
Yes.
doesn't mean what you think it means?
Exactly. It's true, but we are releasing carbon at a much, much faster rate than any of the volcanoes on Earth currently are.
Right.
So that is how carbon primarily gets introduced to the outside, not in the depths of Earth environment. So carbon is released both in the form of rocks and minerals as well as gases from volcanoes. So some of it goes to the atmosphere, some of it stays on the surface of the Earth as rocks. But as we mentioned, those rocks erode into sedimentary rocks. And as we've discussed, those, that weathering, the chemical side of the breakdown of rocks absorbs carbon dioxide from the atmosphere. So the rocks produced by volcanoes do help absorb some of the CO2 given off by the volcanoes. And then both the minerals that break down and the new ones formed by the chemical weathering get buried in the ocean, and that deposits all of that carbon in a place that is not the atmosphere. And so those rocks then get turned into sedimentary rocks, things like those sandstones. Sandstone can have carbonate as one of the cements that hold the sand grains together, or they can just get dissolved into the ocean because the ocean has lots and lots of dissolved CO2 in it. That's what a lot of animals who make shells out of calcium carbonate, which is just about anything that makes a shell in the ocean, whether it's bivalves, crustaceans, corals, they use calcium carbonate to make their skeletons. And all of that is just dissolved in the ocean. So all of those things can sort of use it as part of their life processes, and then they die and form other sedimentary rocks. So sort of a self-contained sort of mini cycle within it. And then also some of that atmospheric carbon can just be absorbed or dissolved into the ocean from the atmosphere. That's a lot of how some ocean oxygen gets from the atmosphere into the ocean. And then all of those new rocks, whether it's a limestone formed by all those shells and things, or whether it's part of that initial, breakdown of some of those volcanic rocks, that can then be subducted down into the earth and melted and then come back out as those rocks or gas later on. So the rock cycle isn't an abstract thing that just sort of happens. This has very real impacts on life. Specifically, if you have a volcano erupting for too long, that's really bad. That's really bad for life. There's been
that sounds really bad for like lots of things.
Yeah, the big thing is, for example, the end Permian mass extinction, as we've mentioned before, lovingly referred to as the Great Dying. It is the worst mass extinction in history. Was caused by a gigantic volcano going off for minimum hundreds of thousands of years. And all of that, and by gigantic volcano, I mean like half of what is now Russia.
Oh, good, but that's very large.
Yeah. And so all of that eruption was just spewing this carbon dioxide into the atmosphere without those other processes that would normally suck it up. It diffusing from the atmosphere into the oceans, the chemical breakdown of a lot of the rocks. If it just keeps producing new rocks to cover those ones, the air can't reach them, if they're buried under other lava, And so it was spewing out the carbon dioxide faster than the Earth's natural processes could absorb it. And among lots of other chemistry things that happen when you have that big of a volcano erupting for that long, cause a lot of global warming. and was really bad for life. Spoilers. For a future episode about the Permian period. And also for what we're doing to the planet today.
Yeah, I was going to say, it sounds like there's some relevance to what that was you're referring to there.
Yeah, just a little bit.
Just a wee.
Yeah. So just wanted to leave off with a practical sort of example of how the rock cycle affects life, using hopefully something that at least most people are sort of familiar with.
Awesome.
And because there's no Fia today,
no Swamp Corner with Fia.
Yeah, no Swamp Corner today, unfortunately. So Fia will hopefully be back with us next week. And I think that's all I've got.
Perfect. This was this was a good way to phrase it at the beginning, like you said, where it was like, this is something you can get as deep into as you want, or, kind of have it sort of a cursory look. I like I like the just kind of the brief explanation and just hey, these are the different kinds of rocks, and then thinking about it as a web instead of a cycle because of all the different, types of rocks there are is it's a cool way to think about it. And I like the way that you prefaced this episode.
Well, thank you. And like I said, especially with things like even, maybe in the future we'll have an entire episode dedicated to each of the 3 rock types. It's like a Sedimentary Rocks episode, an Igneous Rocks episode, Metamorphic Rocks episode. Just because, I could probably use the brush up on it, realistically. But also just to show how complex it is. Like, I tried to simplify it a lot in this episode to be like, hey, you smush some sand together and it makes a sandstone. But that is less than intro level. That's something that most geology professors would assume that you already know. So
we'll do that job for you.
Yeah, absolutely. So we will put those on the list along with, what was the thing you said? Deep sea episode. Yes.
Yeah, but those will be added deep sea, whether it's the biology or geology of just the extreme depths of the ocean. I want to learn something about that.
Sure.
But it will have to wait for another week, because this has been episode 76 of I Wish You Were Dead, a podcast about things that used to be alive. My name is Mike. That is Gavin. We hope to have Fia back next week, but until then, take care, everybody.
This episode of I Wish You Were Dead was written by Gavin Davidson and hosted by Gavin Davidson, Mike Bryson, and Finella Campanino. It was sound edited by Mike Bryson and edited for YouTube by Gavin Davidson. Special thanks to former guests of the pod and to listeners like you.